So welcome to a new class on matrix method of analysis, fourth module of our structural analysis 2. Today we are going to discuss about truss analysis using stiffness matrix method. So consider this truss as shown in figure. The truss element A, B, AC, AD are all connected to a single joint A. So this is a special case of a question in which there is a shortcut method to solve this problem. So the truss members are connected to a single joint. Only for those problems we can solve using this case. That is, there is a special shortcut to find the displacement transformation matrix. Okay, so let's see. Our first step is identifying the degrees of freedom. At a joint B, there is a fixity. So the degrees of freedom is 0. Joint C, degrees of freedom is 0. Joint D, degrees of freedom is 0. Degrees of freedom means ability to move freely. It's a fixed support, so there is no movement available. So 0 is the degrees of freedom here. But at joint A, nobody is preventing. There is no support. So the system can move in X direction. System can move in Y direction. Right. Rotation is not considered since it is a truss element. Truss will only have axial loads. So motion in X and Y direction. So degrees of freedom equal to 2. So these degrees of freedom is represents the number of system coordinates in the truss element. So two system coordinates are to be considered. That is as shown here. System coordinate 1 and system coordinate 2. We take both the system coordinates in tensile nature. Okay. In the question, the system coordinates are given 100 kilonewton is acting downwards. That is, it is hitting the joint A. So it is compressive in nature. Whereas 200 kilonewton is pulling the support or the joint A away. That is, it is tensile in nature. So while writing the load matrix, the 200 kilonewton load is written as positive. That is the first system coordinate. This one is positive, and 100 kilonewton is written as negative because it is compressive in nature, but we considered it as a tensile system coordinate. So we give a negative symbol here. Okay, then third step is element coordinates. We have three elements: element 1, element 2, element 3. Now element stiffness matrix is my fourth step, and the fourth step is for a single truss element, we have derived the stiffness matrix as AE by L. If there is three truss elements, what will be the formula? We assemble the stiffness matrix as done in the continuous beam problem. AE into we if the length are different, then we will get the formula as 1 by L1, 1 by L2, and 1 by L3. The other terms are 0 for the matrix. Right. We write the K assembled as matrix of K1, K2, K3. 0, 0, 0, 0, 0, 0. K1 is equal to AE by L. K2 is also equal to AE by L. Taking AE common outside, we will get 1 by L1, 1 by L2, 1 by L3. The different length values are given in question: 2.4, 1.8, and 1.4. That are the length of each element. This one, 2.4, 1.8, 1.4. This is first element, second element, and this is my third element. Now, my fifth step is that displacement transformation matrix. So here is a shortcut formula to find the displacement transformation matrix for a truss element connected to a single joint. The formula is minus of cos theta 1 sin theta 1, cos theta 2 sin theta 2, cos theta 3 sin theta 3, etc. etc. If there are n number of truss elements, cos theta n sin theta n. Here three truss elements, so cos theta 1 sin theta 1, cos theta 2 sin theta 2, cos theta 3 sin theta 3 becomes a 3 by 3 matrix. Well, now what is theta 1? We have to measure it from this direction. Okay, from here I have to take it anti-clockwise direction to the truss element. See the yellow line, yellow angle shown, theta 1. We have to measure it from here till the first element, that is my theta 1. And from that, similarly, I draw theta 2. Again, I draw theta 3 to the truss element. The angle measured from the horizontal to the truss element in anti-clockwise direction. So this is a horizontal line. So I measure it anti-clockwise to the truss element. Okay, now let's find out these angles theta 1, theta 2, theta 3, for which I use the triangle concept. So see, A, B, C, D, the dimensions 0.84, 1.08 are all given in question. This is a 90-degree, right? So if there is a horizontal line, this is my 90-degree. So consider triangle ACD, this triangle. I have to find the inner angle, this inner angle. How will I find? I know the dimensions, the length I know. So I take sine theta. Sine theta is opposite by hypotenuse. That is 1.08 divided by 1.8. I get theta as 36.87. So why I find 36.87 theta angle? Just go back. I have to find the value of theta 2. How will I find the value of theta 2? From 360, I can minus this 90-degree, as well as I can minus this 36.87 degrees. Then I will get a theta 2 value, right? Then what is theta 3 value from the figure? It is 360 minus 90 degrees. And then what is theta 1 value? I have to minus 90 degrees, 36.87. Also, this angle also I have to measure minus from 360, right? Or else I can find out the whole angle. This angle I can find out. So let's see. Consider triangle ABD. I am going to directly find out this angle. So that angle, I take the I take the triangle ABD, find the angle theta. Sin theta is 1.92 by 2.4, theta 53.13. Hence, the angle from this point to this point, theta 1 equal to 360 minus 90 minus 53.13. Shown here. 360 minus 90 minus 53.13, 216.87. Theta 2 is equal to 360 minus 90 minus 36, 233. Theta 3 is nothing but 270. Substitute the values. I will get displacement transformation matrix as minus of minus 0.86, minus zero point 0.8, minus 0.6, minus zero point 0.6, minus 0.8, 0, minus 1. Now the steps are easy. Now just you can use the calculator to find the answer. System stiffness matrix, K matrix, A transpose dot K dot A. Give these values in the calculator, define it as matrix A, matrix B, matrix C in the calculator. Before finding the final answer, you also defined the load matrix as my matrix D. Okay, now go for multiplication of matrix A into matrix B into matrix C. You will get the K value. From that K value, straight away find out the K inverse and then into your load matrix, that is matrix D. This is my matrix D. You will directly get the answer of system displacement from the calculator. Now, next step is element displacement and then element force. You can skip the step 8 and then directly find the step 9, element force. That is Q is equal to K into small letter q, where small letter q is equal to A into R, A dot R. So substitute all three cases in the calculator. Here the K is element stiffness matrix, not the system stiffness matrix. Element stiffness matrix into displacement transformation matrix into this, R. What is R? System displacement R. I substitute these values and then from calculator I will find the final Q values. This is how we find out. Okay, so you can directly find out it using calculator by using from the steps 6 onwards. So that's it. Thank you.